Hi there, this is Dr. Dell, and this is the third video in the interlude number 3. I'm actually going to use this as an example to discuss with you different things that we do beyond the foundation. Now, I prefer, when solving a triangle with three known sides, A, B, and C, to use the generalized Pythagorean theorem, which yields this formula here. You take these two sides, you take a squared plus b squared, you subtract c squared. And then you divide that by 2ab, and that gives you the cosine of this angle. So then you take the inverse cosine of this number, and that'll give you this angle. You take the sine of this angle, and then that's the correction factor. You multiply times a times b times 0.5, and that is it. And I've demonstrated that on the first two videos, and it's a very, very quick way to solve this triangle. Now, when I went to Wolfram Alpha and plugged in the numbers 3, 4, and 6, to verify or see how Wolfram did it, they came back with the same answer, 5.33, but they also showed it as the square root of 455 divided by 4. That's what this 1/2 up here superimposed means, superscript. It means the square root of 455. And so then the question is, well, how did Wolfram Alpha do it? Well, since there's a square root involved, right away that makes one think about the quadratic equations and the quadratic formula. Now, again, this is not something I cover in the foundation course, which is the practical math course. This is something I would now discuss in Tier 3, where we'd be going through Dr. Simmons' book. And let me show you what I did. It took me about an hour or maybe an hour and a half to come up with this. When I asked myself the question, I said, well, let's solve this without using the generalized Pythagorean theorem or trigonometry. Let's go back and use just pure geometry and the Pythagorean theorem. So here's the triangle A, B, and C. And now I extend this baseline A over to here, this dotted line, and this distance is x. And then this is a perpendicular intersection, so this is 90 degrees. This is the height y. So actually, if we use the usual formula for the area of this triangle, we would have 1/2 base, which is a, times height, which is y. Now that's the formula that's always taught in the standard mathematics class. And of course, the problem is, if we're given a, b, and c, we do not know what y is. And of course, one solution to that is to use the generalized Pythagorean theorem, which is what I like to do. But here's another way to do it. We can use the Pythagorean theorem twice and we'll generate two quadratic equations. For example, we take this triangle, we're going to get that y squared plus x squared equals b squared. That's a Pythagorean theorem applied to this right triangle. And then if we take this larger right triangle, we're going to get that y squared is equal to a plus x, that's this distance here, squared, and that will equal c squared. So now I have two quadratic equations, and if I solve them for y, then I can go back up and use our standard area formula. Now this was what I did, and I'm just showing you the intermediate results. It actually took me 2 or 3 pages of scratch work to do this, and I made a couple mistakes. It slowed me down. I'd say this whole thing took me maybe an hour to do by the time I made my mistakes and fiddled around. The first thing you do is you try to eliminate one of the variables here, and that's easy to do because you've got y squared in both these equations. If I subtract equation 1 from equation 2, the y squareds will go away, and I'll be left with a plus x squared minus x squared equals c squared minus b squared. Now that turns out to be then the x squareds will cancel. There'll be a little linear equation, and you'll get x equals this number right here, c squared minus b squared minus a squared all over 2a. And that turns out to be easy to do. That took me maybe 5 minutes. Now, the next problem then is, what is y? Well, then you come back, I took this equation, y squared is equal to b squared minus x squared. That comes from equation 1. And now I have to substitute in what I know x is. This is this number here. And this is where it gets messy. So I plugged in this for x squared, and I simplified. And that took me probably, I don't know, a page of calculations. It's easy to do, it's just messy, you just have to be patient. And what you end up with is y squared is this number here, 2 times the quantity, a squared b squared plus a squared c squared plus b squared c squared, minus a to the 4th power minus b to the 4th power minus c to the 4th power, and then that whole quantity there, all divided by 4a squared. That is not very hard to do. You're probably looking at for tier 3 student, it's easy to do, and you're probably looking at maybe 30 minutes, 20 to 30 minutes of doing it, particularly if they make a mistake like I did, and have to do it twice, more or less. Once you've got y squared, then the square root of all of this is going to be y, and so then you use the formula zero point 0.5 a times y is the area, and you simplify that, and you end up with this equation here for the area. What's inside the brackets, then you take the square root of that. And what's inside the brackets is basically what was inside the brackets up here, and now you got to divide by 4. And all that works out because I'll remind you that 0.5a is the same as 1/2 a, and that's the same as the square root of 1/4 a squared. That's something you'll need to use when you do this calculation. Now, I got this first. This is where I ended up after, I don't know, 30, 40 minutes of fiddling around. And then I said to myself, well, it's not a bad looking thing. You got a squared, b squared, a squared, c squared, b squared, c squared. There's a little symmetry there. And then you got to subtract these fourth powers. But I wasn't really happy with it. I thought, well, there ought to be a way to simplify this down to make it somehow more aesthetically pleasing. It won't be any different value. And by the way, right at this point here, I plugged in 3, 4, 6 and verified that that turns out to be then the square root of 455 divided by 4. This whole thing on top, when you plug in 3, 4, and 6 for A, B, and C, turns out to be 455. And so maybe that's what Wolfram did. Maybe they used this formula. I doubt it, but they might have. They could have. Now, I fiddled around a little bit, and it was a little bit clever, but not very difficult. And I was able then to change what's inside the brackets into this form. A squared times the quantity b squared plus c squared minus a squared. Notice here now you got the other two variables, b and c, and then minus a squared, and then plus b squared, and then I got a squared plus c squared minus b squared, and then plus c squared, a squared plus b squared minus c squared. So you see a certain symmetry here, don't you? You got a squared here, and that'll be a minus a squared. You got a b squared here and a minus b squared, a c squared here and a minus c squared. All of that, square root, all divided by 4. And that turns out to be this equivalent formula. And by the way, the key to that is a to the fourth is a squared times a squared. And here you've got 2 of the a squared plus b squareds. So you got a squared plus b squared plus a squared b squared. And then you got the same here and here. And when you play it out, with a little effort, you should be able to see how it's pretty easy to go from here to here. And I did that. Now, that's the formula that I came up with. And using the two Pythagorean theorems and the quadratic equations. And I have never seen this formula in any book. As a matter of fact, if any of you could find a book that has this particular formula in it, or this one here for that matter, but either one of these, I would be very interested in knowing that. And indeed, I would be very happy to give you a little reward if you could send me that information. And I would be glad very much to, I don't know, give you something for doing that, just because I find it interesting. So I could even call this, Dr. Dell's formula. I'm not going to because, quite frankly, I don't find this formula as near as easy a way to evaluate as I do the one using the trigonometry. And so I still stand by, and this is still what I would teach in the foundation course until I find something easier. This is what I'll use up here, is the generalized Pythagorean theorem with the trig. And the reason I can do that today is because trigonometry is so easy to use with a calculator. Now, back in the old days, when trig was much harder to use because you had to use trig tables and you didn't have calculators, this is a formula that you might have used because all it involves is squares and square roots. There's no trig involved in this at all. And so that's the advantage this formula has over the one that I now use. The disadvantage is it takes a lot longer to do the calculation. I can kind of remember it, but it isn't obvious where it comes from. This derivation, if you go through it yourself, wouldn't be obvious. Now, I might say I often use problems like this in the upper tiers, tier 3 and tier 4, particularly to challenge the students that are really quite interested in math because it helps in their thinking. What I'm going to show you on the next video then, though, is something that's really quite neat that came out of George Simmons' book. It's even another formula that does not involve trig to solve this that has a name attached to it called Heron's formula, and I'm going to show you that on the next video. But I just wanted to show you how you might do this problem if you didn't use trigonometry. And it is a way to do it, although I think it's much longer and messier and probably not of much interest or value today in practical math. This is Dr. Dell signing off, and I'll see you on the next video where we'll talk about Heron's formula. Bye-bye.